So we're picking up with the piecewise function that we did today in class. We had our piecewise function here that was x squared if x was less than or equal to -2, and then the function turned into x minus 3 when you put in values from -2 to 4, including -2, not including 4, and it was the square root of x when we had x greater than or equal to 4. So we had evaluated the function at 3 by realizing that 3 would be on the piece that had x values between -2 and 4, which would mean we plug 3 into x minus 3 and we got 0. And for 16, we'd be on the piece of the function where we were using values greater than or equal to 4. So we plugged 16 into that piece and got the square root of 16, which was 4. And for one of my classes, I was able to graph it, and the other I didn't get a chance to, so we'll pick up with the graph here. So we talked about looking at each piece on its own, and the first piece of the function occurs for values that are to the left of -2. And so for the values to the left of -2, the function is going to take those values and square it. So if you put -3 in, you would take that and square it and end up with a value of 9. If you put -2.5 in, you would take that and square it, and you'd end up with a value of about 6.25. You're not supposed to put the number -2 into the function x squared because this is a less than symbol, not a less than or equal to. But if you did put -2 into the function, you would be getting a value of 4. And that is what we're going to be calling a limiting value. So I think I should have moved this over a little bit, sorry. So that limiting value is the value that the function is approaching as we get closer and closer to -2. The function value would be 4 if we were able to plug in. And that's what creates this parabola shape. But we have to put an open circle there because when we actually plug -2 into the function, we have to plug it into this piece. So when we're plugging -2 in, it's going into x minus 3. So we're going to get -5 out. And that's the function value that we would put as a dot on our graph. And that rest of that function is a line. X minus 3 graphs like a line, and it graphs like a line with a y-intercept of -3 and a slope of 1. And it's going to be that line up until we get to the number 4 on the x-axis. And when we get there, again, we're not allowed to plug 4 into that function. But if we did, we know that we would get a value of 1. So we're going to put an open circle there, and that's where our line is going to terminate. So that's the second piece of our function. The third piece of our function graphs like a square root, and we can plug the number 4 into that square root, and we're going to get the value of 2 out. We can plug 9 in, and we'll get the value of 3 out, and all in between, we're going to have values of square root that are going to make that graph look like the square root shape, which graphs like the top half of a parabola if you turned it on its side. So there's the graph of this piecewise function. Linear functions are something that you learned in Math 21 as well. And when you were graphing linear functions, you needed to know a slope, like we did up there. We had a slope of 1. You needed to know a y-intercept where it crossed the y-axis, and we had a y-intercept here of -3. So that's what slope-intercept form looks like. There's also a point-slope form of a line that you learned in 21, and that's given here. So an example of the kind of linear function that you might see in business calculus would look like this. If you have a software company that's producing and selling systems at a cost of $55 a copy, and the company has a fixed cost of $15,000 a month, we can express the total monthly cost as a function of the number of copies that we're going to sell. So we're letting X stand for the units that we sell. X is always going to stand for units in our class. So we're going to have a cost that's made up of two different pieces. There's a fixed cost, which is a cost no matter how many units I sell. And they said that was $15,000 a month. That could be like rent or machinery. And then there's a variable cost that depends on how many units I sell. Every unit I sell is $55, so we'll call that 55 times the number of units I sell, which is 55x. And that creates my total cost function. If I were going to graph my cost function, the y-intercept of that would be the 15,000, because if I make no units, it still costs me 15,000, and the cost function is going to head up because every time I sell a unit, another unit, I'm going to be adding another $55 onto my cost. So if I sold one unit, I'd be up here at 15,055. And if I sold 2 units, I'd be at 15,110. So that's how this is the slope of the graph, because it tells me how much it's going to cost for each additional unit. And that's what slope is doing. So moving on to another type of linear function. Sometimes they're not quite so straightforward. For example, in this case, I've got a price for selling raffle tickets. If I price them at $5, I can sell 400 of them. But if I drop the price to $4.50, I can sell more of them. And that's what usually happens. The lower the price, the more people want to buy. And so if we make an assumption, and this is a big assumption, that demand is linear, that would mean that every time I drop the price 50 cents, I can sell 25 more. Because to be linear, we'd have that constant effect of dropping the price, always selling a certain number more. But let's assume that we do say it's linear. To write the equation of any line, all you need are 2 points. And we're going to always assume that our units sold go on the x-axis and our price, which is money, goes on the y-axis. Which means that if I write the first statement of 400 units being sold for $5, the point would look like 400, 5. And my second point would look like 425, 4.5. So I'm going to put the units and match it with a price. So once I have 2 points, I can come up with the slope of the line using my slope formula, subtract my y values, subtract my x values, make a fraction. And so I'm going to end up with 5 minus 4.5 over 400 minus 425. Now you might have been thinking 4.5 minus 5 over 425 minus 400, but it really doesn't matter which way we do it. We're going to end up with a negative answer because the slope of a demand function should be negative. So if you did it subtracted the other way, your negative would be on top. But either way, we're going to get -1 over 50 as our slope. And so once we have the slope and we have a point, we can write the equation of our line by using y minus y1 equals m times x minus x1. And so we would have y minus, I'll use the first point, 5, -1 over 50 times x minus 400. and that is the demand curve, or in this case, line. But we could always simplify it a little by distributing and then combining, moving my 5 over to the other side. So when I multiply these, I'm going to get 8, and then I could add the 5 to both sides and call it 13. And this is my demand function, where y is representing the price. So that's, again, a big assumption. Most demand functions are drawn as a curve because things don't always happen at the same rate. Dropping the price from 5 to 450 is not going to have the same effect as dropping it from $2.50 to $2. And so usually we'll draw it like a curve because it acts like a curve. This is a big simplification. Quadratic functions. Sometimes functions curve when we draw them instead of being straight lines, and sometimes that curve happens like a parabola. So in supply or demand functions, again, we don't always have the same, a constant kind of rate of change. So if the rate of change curves, it might be more like the shape of a parabola. And you know you have a parabola when you have an x squared in your function. And you can use a graphing calculator in this class, in this Math 110 class, to be able to graph your curves and find your zeros. But we'll be talking more about that in class because I left my graphing calculator at work. Polynomial and rational functions then would be the next step. Sometimes the exponent on your function isn't just a square. If it could be a cube or it could be a fourth power. So the higher that you let this degree be, the more terms you might have in your polynomial. And they're all going to graph different ways depending on what the exponent is and the coefficients. And you worked on that some in Math 22. And we'll be touching on that more in 110. A rational function occurs when you have two polynomials and you make a fraction out of them. And you just have to remember, like we talked about in class today, that anytime you have a denominator that's a polynomial, you have to make sure that you look at the domain and think about the domain. So in this case, x can't be 1 or -1 because that would make the denominator 0. And the way we would write that expression is by using our interval notation and going from -infinity to +infinity, but we are dropping out the two values that we don't want to have in that set of numbers. And so this is what it looks like in interval notation. And then finally, the rest of the material from today, we can have a function like we have here in this example, a cost-benefit model for removing a pollutant from the atmosphere. So x is the percentage of the pollutant that you want to remove, and the function f of x is measuring the cost of that. So if I want to remove 50% of the pollutant, then I would be plugging the 50% in where the x is. Although the way x is written here, I'd really be plugging 50 in because they're going to count the percent part. They're going to measure the percent part by just dropping the percent. So this is what the domain is telling me. It doesn't say that I go from 0 to 1, then I'd use 0.5. It says I go from 0 to 100. So if I were to remove 70%, it would look like plugging 70 into my function. And I'd have 50 times 70 over 105 minus 70. Or if I want to do 90, I'd have 50 times 90 over 105 minus 90. And then same thing for 95. So again, I don't have my calculator with me, but I'm assuming that you could plug that in and simplify those to find out the cost for that to happen. And then the final thing that I had wanted to get through today, which I didn't, is the idea of an absolute value. So this is something that you saw in Math 21. Saw it again in Math 22. Absolute value are piecewise functions. So absolute value, if you think about it, is just like this problem that we had earlier. It just is not written out that way most often. Most often we say f of x equals, and we use these vertical lines around the x to say absolute value. But what we really mean is that you can't really tell what the function itself is, what f is, without knowing what kind of numbers you're plugging in. So as long as you use 0 or greater for the values you're plugging in, absolute value is just doesn't do anything. Whatever you put in, you get out. That's the line y equals x. But if you decide to plug values that are negative in to an absolute value, well, then that does do something. It takes negative numbers and it makes them their opposite. So that's this line. Y is